so we're on to part 141 now. This is line 18A, a3y2. Dark matter, neutrinos, argon, xenon U235, which stands for uranium. Formula, UFO 5G Wow Seti. This is where you're going to get into the actual formula ideas that I come up with based on the research that I've found. What I'm basically doing is throwing together any keywords that seem to always come up together all the time, and to me that's some sort of message. So then I'm going to give you some ideas of how to mix and match them together, and I hope you get some good results from it, okay? I am going to be reading some stuff though, because again, there's terms here that I'm not familiar with, so please bear with me. So this is the Wow Seti radio signal, and the ARDM experiment came up, and it's a search for dark matter in the universe with liquid argon. It's from Zurich. There's the names there. Sultan Institute or whatever. Sorry. Astronomical observations give strong evidence for the existence of non-luminous and non-baryonic matter, presumably composed of a new type of elementary particle. A leading candidate is the weakly interacting massive particle, WIMP. If they exist, which we know they pretty much do, WIMPs should form a cold thermal relic gas. Now, I found that interesting because it says cold thermal relic gas. I don't know if you can use that in with the cold plasma or not. It's just an idea. Which could be detected via elastic collisions with nuclei of ordinary matter. The detection of these WIMPs is based on the capability of measuring the recoils of target nuclei with kinetic energy in the range of 10 to 100 keV. The signal is therefore quite elusive and is expected to be a rare event given the weak coupling between WIMPs and ordinary matter. A better understanding of the DAMA, the DAMA, which is another type of result, or alternative, the coverage of large fractions of the remaining theoretical parameter space of theories accommodating WIMPs. Example, supersymmetric extensions of the standard model can only be achieved at the cost of improved detector technologies that are compatible with our large target masses. Current experimental results from CDMS, Zeppelin, and Edelweiss, those are all letters, of course, probably abbreviations for other letters, exclude cross-sections above a few 10 to 42 centimeters too. Noble liquid detectors using xenon or argon can efficiently act as targets for weakly interacting massive particles, WIMP detection. Again, I've pulled phrases that stand out for me. This isn't how it was written, it's all little phrases, okay? Xenon or argon provide a high event rate because of their high density and high atomic number, and large target masses are readily conceivable. They have high scintillation and ionization yields because of their low ionization potentials. Both scintillation and ionizations are measurable and can be used to very effectively discriminate between nuclear recoils and gamma electron backgrounds. So I got another little graph here for you. It talks about 100 event ton per day, 1 event ton per day, and 1 event ton per 100 days. And that's the true recoil energy, number 30 keVR. Okay, and there's the WIMPs down there. And I can't read all that little print down there. So the use of noble liquid gases to detect WIMP dark matter is currently the subject of intense R&D carried out by a number of groups worldwide. In these detectors, one relies on the simultaneous detection of the ionization charge and of the scintillation light produced during a nuclear recoil event. A main subject for any detector is the method of the readout for the ionization and scintillation. Currently, the Xenon, Zeppelin, and Warp designs rely exclusively on photomultipliers or PMTs for their readout. The possibility to directly detect the ionization charge is less well developed, although it might provide alternative and potentially large benefits. So they're looking at theoretically what this type of power they can get from this, by the looks of it. Given the low energy thresholds necessary to effectively detect WIMP signals, this method, however, requires the charge to be amplified before it reads out. It is read out, sorry. While amplification is not possible in the liquid argon phase, it can be achieved in the vapor, in equilibrium on top of the liquid, although operation in this context precludes the inclusion of a common avalanche quenchers since they will condense in the liquid phase. And that's at neutrino.ethc.ch. February 19th, 2012, my thoughts. Looking at this quote, while amplification is not possible in the liquid argon phase, it can be achieved in the vapor in the equilibrium on top of the liquid, although operation in this context precludes the inclusion of common avalanche quenchers since they will condense in the liquid phase. My thoughts continued. Earlier I mentioned that you spray the ice-cold neutrons and particles that have collided with a mist of water at a different temperature, a bit warmer, so that it will show up. Keywords in this quote: xenon or argon provide a high event rate because of their high density and high atomic number, and large target masses are readily conceivable. So I googled xenon to see what type of particle it has. Xenon is a chemical element with the symbol Xe and atomic number 54. The element name is pronounced xenon. A colorless, heavy, odorless, noble gas. Xenon occurs in the Earth's atmosphere in trace amounts. Although generally unreactive, xenon can undergo a few chemical reactions, such as the formation of xenon hexafluoroplatinate, the first noble gas compound to be synthesized. Naturally occurring xenon, it consists of 9 stable isotopes. There are also 40 unstable isotopes that undergo radioactive decay. The isotope ratios of xenon are an important tool for studying the early history of the solar system. Radioactive xenon 135 is produced from iodine 135 as a result of nuclear fission, and it acts as the most significant neutron absorber in nuclear reactors. The reason I'm reading all this is just so you know, based on my theories and the formulas I'm coming up with, I look and Google them to see whether they're possible or not, and according to these keywords that I find, it looks like they are. The first excimer laser design used an exodimer molecule Xe2 as its lasting medium, and the earliest laser designs used xenon flash lamps as pumps. Xenon is also being used to search for hypothetical, weakly interacting massive particles, and as the propellant for ion thrusters in spacecraft. So this is very, very, very important, because we want our propellant for an ion gun. I have an ion sputtering gun that I found as one of the inventions. So this xenon obviously is going to be part of the equation, okay? So February 19, 2012, and at 9:21 p.m. I did some reading, and then at 9:52 p.m. I finished writing. I start writing and then I stop and then I start again. So my thoughts: xenon is a byproduct of fission of uranium-235. I have another formula idea for you now. Okay, U235 comes up in an earlier line of data, and we're going to use that in the process of exciting the neutrinos, plus liquid argon gas, plus the laser beam, plus the turbine invention, and plus the sputtering gun invention, plus leptons. So, quotes from xenon data. Naturally occurring xenon consists of 9 stable isotopes. So I wanted to know what those were. So I got radioactive xenon 135 is produced from iodine 135 as a result of nuclear fission, and it acts as the most significant neutron absorber in nuclear reactors. So that's the other key word, the neutron absorber in nuclear reactors. So you're looking for something to absorb the neutrons. The noble gases are a group of chemical elements with very similar properties. Under standard conditions, they are all odorless, colorless, monatomic gases with very low chemical reactivity. The 6 noble gases that occur naturally are helium, neon, argon, krypton, xenon, and the radioactive radon. And it's on Wiki on a noble gas, okay? This is the tags for this video. Okay. So that's the end of that one. And we got some more formulas coming up for you soon.